All right. So today we are going to discuss about lecture 6. So this is again the physics of semiconductors, but today we are going to focus on the carrier transport. That means how the electron or the holes move in the system. The previous lecture we talked about the carrier statistics. That means we talk about the electron or the hole density, and here we talk about how they move. Eventually, we can get the current, because current depends on two factors. One is how many carriers are there, that is the density, like the electron density N or the hole density P. The other factor is how fast the carrier move. So this is what we are going to discuss today. So how fast the carrier move. So that is a carrier transport. This is a reference chapter, and this is a recorded lecture from the last spring. Alright, so the first mechanism for the carrier to move is this drift. And drift is under the electric field. Drift is the motion of the carrier caused by the electric field. So in the semiconductor, we have two types of carriers. One is electron, one is a hole. And in this example, if we think about the hole, which is positively charged, then we have the electric field applied externally to the right. So the hole will statistically move to the right after some time. So then this hole will move along the electric field. So this will cause the drift of the current. But the path is not a straight line. You are actually going through those so many scattering events. And this is the scattering. This is similar as what we discussed before in the lecture 2. The electrons will scatter with the atoms in the metal. So here is a similar situation. Holes will also interact with, for example, the dopant in the silicon. Then it will have the scattering. But overall, the hole will move along the electric field. And then this motion is called drift. And the tau m here is defined as the average time before the scattering. So that is from scattering 1 to scattering 2, those two events. If we take the tau m time, then this is the average time between those two scattering. And then we can think about the momentum of this drift motion. The momentum if you recall the Newton's law, is given by mass. The mass multiplied by the velocity. And then it's the same as the electric force applied during this tau m period. Here we talk about the hole, so we will use P to represent the mass for the hole, and this tau mp is the average time between scattering for the hole. So this is the momentum in the Newton's law, and then we can derive the velocity as a function of the electric field. And then we can again define those three parameters as the mobility mu p for the hole. So here the conclusion is the velocity is proportional to the electric field, and this coefficient is called the mobility. And this is for the hole. Similarly, we can derive this for the electron, and actually we have done that in the lecture 2 for the electron. So the velocity is again proportional to the electric field, But here we have a negative sign because the electron moves to the opposite direction of the electric field. So we have the negative sign here. And here we have the mobility for electron and mobility for the hole. They may be different in terms of the values in the silicon. But overall, the principle is very similar between the electron and hole. And in the lecture 2, we only have the electron. Why is that? Because in metal, we only have electron. But here, lecture 6, we are talking about the semiconductor. And you have learned that semiconductors have two kinds of carriers. One is electron, one is hole. So you need to consider both. So any questions here? If you have questions, then please type in. What is T and M again? M is a mass. Effective mass. And this tau is the time between two scattering events. So this is Newton's law. The momentum is given by mass times velocity, and also it's the same as the force, electric force, and then this electric force is exerted by a period of time, then that will cause the momentum. Any other questions? Is the mass of a hole reactive? That's a good question, but the mass is always positive. So the mass for the hole is also positive. But the mass for hole and the mass for electron may be different. And this is the reason why the mobility for the electron and hole are different. So this is what we are going to see in this slide. So again, the velocity of the carrier in principle is proportional to the electric field. And this coefficient is the mobility. Of course, then depends on the electron or hole, we should take the absolute value. And this mobility has this unit, centimeter square divided by volt and second. So this is the same as we see in the lecture 2. So basically, mobility tells you how fast the electron or the hole can move under the electric field. And this table shows the representative semiconductors. And in this case, it's the intrinsic semiconductors without doping, undoped. And we have mu n and mu p for electron and hole. So in silicon, the electron's mobility is 1400, and the hole's mobility is about 470. So you can see that the mobility mu n is larger than mu p. And this is generally true in all the semiconductors, not only silicon, but also others. The reason goes back to the effective mass. So the in silicon and also in other semiconductors, the electrons are lighter in mass, so they move faster than the hole. So in other words, electrons move faster than the hole. That's simple. Electrons move faster than hole. And for different semiconductors, the mobility value actually change a lot. So here we see other semiconductors. For example, this germanium is also group 4 element, and the mobilities are higher. And then if we go to this grade 5 semiconductor, like this gallium arsenide or indium arsenide, So why is this 3, 5? So because gallium is a group 3 element, and arsenic is a group 5. So this is called 3, 5 semiconductors. So in the 3, 5 semiconductors, typically the electron mobility will be very high. For example, in indium arsenide, the electron mobility can be up to 30,000. So this is very fast for electrons. So that's why the 3, 5 semiconductors are typically used in high-speed applications. So like the circuits used in the microwave applications where you have very high frequency, then you want the electrons to move fast, then you may want to use a gallium arsenide or indium arsenide or 3-5 semiconductors in general. But for digital computing, like your microprocessor, then silicon is good enough. And also other reason is silicon wafer is cheaper in terms of the fabrication cost. So silicon is good enough for the typical like gigahertz clock frequency for your digital computing. But if you are talking about the microwave or the millimeter wave, the terahertz communications, in those circuits you may have to use the 3-5 transistors. So this is for special applications. Any questions? Alright, so here the key conclusion is that the mobility mu n is larger than mu p. So this is very important because later as we learn the circuit operations, we will know that the n-type transistor is faster than the p-type transistor because the mu n is larger than mu p. So we need to do something from the circuit design point of view to compensate the difference between those two transistors' speed. So the reason comes from here. The mobility is different. And then let's look at the, let's say, the causes for the degradation of the mobility. That is the scattering by the dopant. So for example, in the n-type doping, you have the arsenic, for example, as the donor. As we discussed, the donor gives out one electron, but the system is charge neutral. So the donor nucleus will carry positive charge. So here this arsenic ion will have the positive charge. Then when the electron move under the electric field, then the electron will be scattered by the dopant because of the Coulomb force here. And the electrons will change the S. So this is the like slowing down of the electron. And this is the cause of the degradation of the mobility. And you can imagine that with higher and higher doping density, you get more and more of this kind of arsenic ion. Then the electron scattering will be more frequent. So the mobility will decrease. This is true when you look at this graph. This is the experimental data measured in the doped silicon. The mobility for electrons and holes as a function of the doping density. For n-type doping, you know, is Nd. For p-type doping is Na. So for the n-type doping, you care about the electrons because electrons are majority carrier in the n-type. And without doping, it starts from like 1400, as we see in the previous table. As you increase the doping density, and if you recall the typical doping density we use is about 10 to the power 15 here to like 5 times 10 to the power 18 here. So in this range, you see that as you increase the doping density, then the electron's mobility will decrease from 1400 to around 200. This is because more scattering caused by those higher doping. And similarly for the hole, it will degrade the mobility from this 470 to below 200 if you increase the Na, the acceptor doping density. Any questions? So how is the mass of a hole defined? Okay, so this is a good question, but we are not going to discuss that in this class. It's very complicated. So the mass of the hole is a little bit tricky because hole is not real, right? It's a conceptual particle. It's a vacancy of the electron. So it's hard to define the mass in the classical way. So it's very complicated. We are not going to discuss that in this class. But I know the answer. You have to go to the so-called energy and momentum EK diagram and then look at the slope of the EK diagram to get that. But we are not going to talk about those in this class. So you can ignore this. But what you need to know is the mobility for electron is higher than mobility of the hole. That is what you need to know from this class. If you want to know the exact reason, you have to go to the quantum mechanics. All right. So here, let's look at one simple example of the drift current density. So the drift current density, for example, in this p-type semiconductor, we care about the hole because hole is a majority carrier. And the current density, Jp, P represents the hole, equals to QPV. So why is that? Q is the charge quantity, it's a basic physical constant. It is 1.6 times 10 to the power negative 19 coulomb. That is a charge one electron carry. And then P is the hole density. This V is the velocity of the hole. So P will be 15, in this example, will be 10 to the power 15. For example, if you dope the Na with 10 to the power 15, then you will get P the same as acceptor density. So 10 to the power 15. And then in this example, the velocity is V. Sorry, this velocity V is 10 to the power 4. So you just plug in the numbers, you will get the current density, Jp, is 1.6 ampere per centimeter square. So this is the current density. That means the current passes through this cross-sectional area. If the cross-sectional area is 1 centimeter square, then the current will be 1.6 ampere. So here the current density, as we discussed at the very beginning of today's lecture, depends on two factors, right? One is the hole density, P. One is the velocity of the hole. Why is that? Because current, you know, how many holes are there and how fast they move. So basically those two factors here. This is in the p-type. We care about the hole. Of course, in n-type, then you will have the Jn. Similarly, QnV, you will change the p to the n. Then this v is the velocity for the electron. The only difference here is you have a negative sign for the electron, because the electron flow and current flow by definition is opposite. But you have the electron's velocity is this mu, negative mu n e for electron. So if you plug in that, then those two negative signs will cancel each other. So still the electron current density is Qn mu Ne, and hole's current density is Qp mu Pe. And then the total drift current is the sum of the electron current and the hole current. Why is that? Because if you think about electron and hole is a pair, then you have hole here, electron here, then if you have electric field, then you know the hole will move to the left, electron will move to the right, then you should add those two current components together. So if you do that, then you add those two together, then you will get this equation. And from the macroscopic view, from the Ohm's law, you know the current density, drift current density is a sigma E. The sigma is the conductivity, and E is the electric field. I think you have done the homework on this. So this is from the macroscopic view, and then we have the microscopic view here. So this is very similar as the lecture 2 when we discuss about the electron in the copper, the metal. So here you can get the conductivity, sigma equals to Qn mu n plus Qp mu p. So if you compare to the lecture 2, the only difference is that we have one more term here. This is because in the semiconductors we have both electrons and holes, but in the metal we only have the electron. But in practice we have the doping, right? So if we consider n-type semiconductor, actually you can ignore the hole in the n-type. So sigma is basically determined by the electron only. And in the p-type, then you can ignore the electron, so it's hole only. Only in the intrinsic semiconductor where the electron and hole density are comparable, then you can consider both. But in the real applications, we always will have n-type or p-type doping. Then you can consider just one type of the carrier. And then 1 over sigma is the resistivity. 1 over conductivity is resistivity rho. This is by definition. All right, any questions? Okay, so then let's move on. And here we show the relationship between resistivity and the dopant density in the silicon. And this is the experimental data measured from the doped silicon for both n-type and p-type. So here we have the dopant density. Let's say typically we have 10 to the power 15 up to like 5 times 10 to the power 18. So in this range, then we look at the resistivity change will be from here to roughly here. So by changing the doping density, we can change the resistivity by several orders of magnitude. And from the previous slide, you can derive the rho is 1 over sigma, and the sigma is for n-type, you know, is Q n mu n. This is for n-type. And for p-type is 1 over Q p mu p. This is for p-type. And this dopant density, you know, will determine n for the n-type. And the relationship is almost inversely proportional. Why is that? This is rho, and then this is 1 over n, but it's not a straight line in this plot. because if it's inversely proportional, then in this kind of plot, you will see a straight line here. The reason is that this mu n also depends on the doping, right? The mobility, as we discussed in one of the earlier slides. The mobility here, this mu n, also depends on the doping density. So you need to consider that as well. And then if you have considered those, then you can have this relationship. So let's look at one simple example. So this is to determine the resistance of doped silicon. So if you have a piece of doped silicon, and the doping density is 10 to the power 17 for the arsenic. Arsenic is group 5. So you know this is n-type doping. So the Nd is this 10 to the power 17. And you know this will be the same as the electron density, because one donor gives out one electron. And then if we consider a piece of silicon with this n-type doping, this is like 1 micrometer long and 0.1 micrometer square in the cross-section area. So the question is, what is the resistance of this piece of silicon? Okay, so what we can do here is to find out the resistivity first. So from this doping concentration, then the resistivity can be found by this graph directly. So it's 10 to the power 17, and then it's n-type, so it's here. And this is a little bit smaller than this 0.1. This is about 0.1, so this is a little bit smaller than 0.1. And if we read accurately, it's 0.084 ohm times centimeter. And then for the resistance, we just plug in the resistance formula. Resistivity times L divided by the A. This is L, this is A, the area. And then we just plug in the numbers, and then we need to change the unit to be a centimeter. As we discussed in this class, the length will use the centimeter as the unit. So if you do that, it will be like 8400 ohm in this case. So any questions? Got one question, because it was doped, it is n-type. No, doping can be either n-type or p-type, but in this example it says it's arsenic, and this is group 5 element, so that's why this is n-type doping. Alright, so let's compare with the metals. So the doped silicon compare with the metal. And this table is from the lecture 2. We talk about the alumina and the copper, and we have their mobility and the electrons density, and then we have the resistivity. And you know the resistivity is 1 over Qn mu. And in the metal, you only have the electron, so this mu is mu n. So you have the mu, you have n, and Q is a physical constant. And then you get the resistivity. So it's pretty small for the metals. And then for the silicon, then depends on the doping. Okay, the silicon's mobility depends on the doping, as we discussed earlier. So for, let's say 10 to the power 15, this is a p-type doping. Let's say this is a p-type silicon with a doping density 10 to the power 15, which is a very light doping. And then the mobility is 470, or let's say roughly 500. And then what is the resistivity for this p-type silicon? Then we can consider p-type. Then you only need to consider the hole is 1 over q, hole density p, and mobility mu p. And then the mobility mu p is 500, and the density p is 10 to the power 15. So we just plug in the number here, and you know q is this 1.6 10 to negative 19 coulomb. So it's a physical constant. And then you can get the number here. Similarly, you can do the n-type doping in this example. But here we have a very special example where the n-type doping density is pretty high. It's 5 times 10 to the power 19, and in this case we call it heavily doped. This is higher than the normal range when we do the doping. The reason is that we want to make this very conductive. So this is no longer like a traditional silicon semiconductor. It's more like an alloy of your dopant and the silicon. So this is very heavily doped. And if you want to get the resistivity of this one, similarly, it's rho equals to 1 over q. This is n-type. It's n, the electron density n, and which is the same as this nd, and then mu n. And in this case, the mobility is much less. Why is that? Because you have so heavy doping, then your mobility will degrade or not because of the scattering. But even though the mobility is degraded, you have very high doping. So overall, this resistivity can be reduced or not. So if we plug in the numbers and then calculate that, then this is the final answer. It's about 1.25 10 to the power 7 in this very lightly doped p-type. And then for the heavily doped n-type, in this case, it's 1.25 10 to the power 3. So as you can see here, this one is close. Of course, it's not the same as metal because this is still semiconductor. But with a very heavily doped silicon, you can approach the metal resistivity. Otherwise, the normal semiconductor will be like, let's say, 6 or 7 orders of magnitude higher resistivity than the metal. So it's quite resistive. But if you heavily dope, then you can lower down the resistivity by, let's say, 3 or 4 orders of magnitude. Now this is closer to the metal. Then this is and between the metal and semiconductor. So here we have an application for this kind of heavily doped silicon. That is to use it as local interconnect, or in many cases, we make it as a contacts of the device. So later as we learn the MOSFET structure, the transistor structure, the transistor will have, let's say, 3 terminals or 4 terminals. Those terminals means the contact between the metal and the semiconductor. To reduce the contact resistivity, we typically need to heavily dope the silicon to make it as an interface between the metal and the normal semiconductor. But between, we need an interface. This interface is typically this heavily doped silicon because it's kind of metal. It's not as good as metal, but it's approaching metal. So it's an interface between the metal and the normal semiconductors where you have the doping maybe in the 10 to the power 15, 10 to the power 16. Any questions? So got one question. Why isn't the x-axis evenly spaced? and which groups are n-type and which are p-type. I think you are referring to the graph, this one. So the lower curve is n-type, the higher curve is p-type. And the x-axis, this is in log scale. Okay, this plot, the x and y is in the log scale. So in the log scale, if you draw 1, 2, 3, 4, if you think about, let's say here, this is 1, this is 10. If you draw in log scale, then 2 will be here, 3 will be here, so it's not evenly spaced. This is because you draw it in log scale. Okay. And then the other question is, you mentioned that heavily doped silicon has lower mobility, but the formula for mobility doesn't include any term related to the doping density. Could you explain that? Okay, so the mobility actually depends on the doping density. This is what we experimentally measured from the doped silicon. So you see the mobility will decrease with the doping. And the reason is from the scattering. As we discussed, you have more doping, then you have more frequent scattering. So the mobility will decrease. And if you want to go back to the mobility equation, so here, what will change is that this scattering, let's say the time between two scattering, this tau, as if you recall, we define this as an average time before scattering, right? So if you have higher doping, then that means those two scattering will have less average time in between. So the mobility will be lower. So if you go back to the origin of this problem, then that is how you explain the mobility decrease with higher doping. So higher doping, more frequent scattering, and the time between those two scattering will decrease. So that's how you see in this mobility equation. Okay. All right. So, okay, let me stop the first half.